I'd like to present some data from the Explorer 45 satellite that seems to be directly relevant to the hot ring current plasma interaction with the cold plasmaspheric plasma. These data are from S-cubed, or Explorer 45. It was launched on the 15th of November 1971 into an orbit having a 5.24 Earth radius apogee, a 220 kilometer perigee, an inclination of about 3 degrees south, and an orbital period of 7.8 hours. The fact that we're only 3 degrees from the geographic equator means that we're always less than 15 degrees from the geomagnetic equator. Complete pitch angle distributions were obtained by sectoring the satellite spin into 32 pieces. So we have 32 samples in 360 degrees. The pitch angle distributions, therefore, are a reasonable approximation to the equatorial pitch angle distribution. The energy range from 1 kilovolt to 800 kilovolts for protons was covered in 28 steps. From 1 kilovolt to 560 kilovolts was covered in 20 steps for electrons, and today we're going to concentrate only on the protons. The orbit is shown on the board. On its outbound pass, the satellite crosses the dusk terminator at about an altitude of 3.5 Earth radii, as it does on its inbound midnight pass. Apogee is at 2100 hours local time. In the first slide, is the pointer here? There it is. We show the magnetic activity of the period of interest. This is December 1971. There are 2 sudden commencements occurring on the 16th and on the 17th. 5 high-latitude magnetograms are shown just to show what substorm activity looked like at this time. Explorer 45 orbit coverage is shown in this particular bar graph. We'll show data from orbit 97, which is a pre-storm quiet. We'll concentrate on orbit 103, which is a recovery phase orbit, and for completeness we'll indicate some main phase data from orbit 101. I don't at all understand the injection process. I think we understand the recovery phase, so we're going to emphasize recovery phase effects. That is, after the ring current became symmetric. This is now orbit 102. It's a different recovery phase orbit. This is at an L value of 5.4 Earth radii. We've started the rounding distribution at the higher energies. The lower energies are still flat, and you'll see that the samples that are taken right at the very smallest pitch angles we measure show drops that range anywhere from factors of 2 to 5. Now, the fact that our angular aperture plus the angular scan during our pitch angle scan is significantly larger than the loss cone, the fact that we see a drop is clearly indicative of a very empty loss cone in this flat top type of a distribution. We are left then with looking at data of this type, and I want to repeat, I guess, one thing. Every recovery phase orbit, from orbit 102 through orbit 111, when we got back to pre-storm values and the plasma pause was never exited by the satellite, every recovery phase orbit shows this basic pattern in its overall transformation from the flat to rounded distribution, as well as the empty loss cone when the pitch angle scan is sufficient to see it. So we do have 2 experimental observational facts during recovery phase in this storm. That is that we do see a transformation from a flat top to a rounded pitch angle distribution that has an altitude dependence such that the transformation takes place at higher altitudes for higher energies. The second one is in the region of the flat top distribution. There seems to be an empty loss cone. All the data we've seen are from the inbound orbit of S-cubed. During recovery phase, the outbound dusk orbits show the same pattern. One thing that I didn't mention in the previous slide, and that is that if you go to a given altitude and look at the energy dependence of the evolution of the pitch angle distribution, you find that as you go to higher energies, the width of the flat top becomes narrower. The conclusion we come to, based simply on these experimental facts, is that outside the region of the rounded pitch angle distribution, the symmetric ring current recovery phase is about a perfectly stably trapped particle population as you want to find in the magnetosphere. There is 0 or negligible loss due to pitch angle scattering, and that as this particle population is traced to lower altitudes, you enter a region of weak to moderate pitch angle diffusion, which is exemplified by the rounded distributions. The reason why we categorize it as weak to moderate is, first of all, the loss cone is not full as you come down to lower altitudes. And secondly, if you stay within a given region of space and have a flat distribution on one orbit, when you come back around on the other orbit, that will have transformed into a rounded distribution, so that gives us a time scale of less than 7.8 hours to go from flat top to rounded. So it's a weak to moderate pitch angle diffusion process that seems to be excited. We've tried to summarize this in a schematic model of the recovery phase, where as you go out in Earth radii, in the inner regions you have a fairly stable plasmasphere. You have a plasma pause region because each particle picks the appropriate value of b squared over n at which to start diffusing. And the S-cubed observations indicate that there's a region just above the plasma pause region where the ring current plasma is stable. It transforms into a moderate diffusive mode unstable to ion cyclotron generation in this region of the plasma pause. High altitudes transforming at the high energies transforming at the high altitude edge, low energies at the low. A resonant energy equation based on the S-cube data is shown here. And by inference with low altitude measurements above the Explorer 45 apogee, which is 5.2 Earth radii, there may very well be a strong diffusion region called the plasma sheet, which has an unknown wave mode producing the instability, where you would observe an isotropic pitch angle distribution. The low altitude observations can be placed consistently into this picture by simply allowing for field line expansion during the storm. Thank you.